Hi, so now we're going to start with question 5 of the review worksheet. So basically this problem, we have here a grid world like environment, and you can think of this as an MDP. The description of the MDP is here, but you can also see it visually over here. Basically it has this kind of circular structure, and all of the transitions that you can make are represented by these arrows, and the rewards are given by the numbers on top of the arrows. You also have these two ladder squares and two slide squares, and you can see that you get a positive reward when going down these slides, and you get a negative reward when going up the ladder. So the first part is asking us, part A is asking how many deterministic policies are possible for the MDP. So firstly, why is it specifying deterministic over here? Well, that's because, if we allow for randomized policies, then the answer is always going to be infinite, right? Because you can always specify the probability P of taking any particular action arbitrarily. It can be any real number between 0 and 1, and so there's infinitely many policies. But deterministic constrains us in that for each of these states, we need to have exactly one action which is associated with that state, and that's why we have this constraint over here. Okay, so how can we approach this? Basically, we want to think about this like a counting problem. So we have, each of these boxes here is a state, and if we fill in each of them with how many actions you can possibly assign to that state, for example here, from this square you can go left or you can go right. So there's two possible actions. From here you can go left or right, two possible actions, and that's true for basically most of the squares, including these ladder squares. The only ones for which it's not true are this one, and this one. So for each of these, you can see, looking at these arrows, they each only have one possible action you can assign, right? All the others have two. So all of these, you can think of them as being filled in by 2, right? And so on and so forth. Okay, so how do we find the number of policies? Well, a policy, recall, is just a function which maps each state to an action. So this is what the function looks like, right? And so how many policies can there be? Well, you just multiply the number of actions that you can assign to each of the states. So it's going to be 2 options for this, 2 for this, 2 for this, and so on and so forth, and 1, 1, 1 for each of these. And you can count this and check. It turns out that there's 11 of the squares which have a number 2 in them, and there's going to be 3 which have a 1 in them. So basically it's going to be 2 to the power 11. Technically it's this times 1 times 1 times 1, but that's the same as 2 to the power 11. And that's it for part A. Okay, so the next part, which is part B, is basically, we have this table where it specifies the quantity which we want to calculate, as well as the value of the discount factor, as well as what is the start state for each of these values, and we're trying to fill in this table. Notice that there's 2 kinds of values here. There's the V values as well as the Q values, and the purpose of this problem is, note that it says you should not need to do substantial calculation here. So the idea here is you're not actually supposed to perform value iteration or Q learning for the 10 iterations that you might suspect from seeing V10 over here as well as Q10 over here. Of course, doing 10 iterations manually would take quite a bit of time. Instead, the purpose of this question is to get you to be able to intuitively figure out what these quantities are based on the MDP we have up here, as well as the all the actions and rewards which we can see up here, right? Before we start, I think it's useful to revise the definition of what each of these things means. So in particular, whenever we have something like V sub K superscript asterisk of a state S, what does this mean? This means, so this is a number which is the expected future reward of an agent which is acting optimally starting from state S after K time steps, right? So I'll just repeat that again. The star over here indicates that we are an optimal agent. The S refers to the start state, and K refers to the number of steps in the future that we are looking. And this entire thing is the expected reward of such an agent, right? And that's the definition which we're going to be using to fill in this entire table. So let's start with the first one. So V sub 3 star of S as the expected future reward of an agent, in this case starting from state A after 3 time steps if it acts optimally. Okay, so let's go back up here. Which one is state A? It's this one. And basically the question we have to ask ourselves is, what would an optimal agent do in this scenario? And we can start by kind of just plotting out a few different paths that an agent might take. So it might start from A, it might go over here, that's 1 step, and then 2 steps, and then 3 steps. And at this point, how much reward has it accrued? Well, just 0, because all of these were transitions with reward 0, right? It could have done something else. It could have gone here, and then back here, and then back here, or something like that, in which case it would have still got 0, right? So you can see that a bunch of these things end up giving us a total expected future reward of 0, right? But is there anything which gives us something non-zero? Yes, there is. In fact, if you go here and then 1, 2, 3, that takes us to this square. That's 3 transitions. And what's the total reward? Well, it's -1 because of this -1 over here, right? Okay, so you might say, this is one trajectory which has a non-zero reward, and so we can say that the value is -1. It turns out that's incorrect, right? Because we're talking about what is the expected future reward of an optimal agent. And an optimal agent would not take that path. Instead, it would either, like maybe it would just go right, 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 or it would keep oscillating like this, or something like that. The point is, an optimal agent would not take the path which gives a reward of -1. It would choose any of the paths with reward 0 over that one. So our answer here is just equal to 0, right? Okay, what about the case when the starting state is E? So if we're starting from here, once again, you can kind of, you can think about what are the various paths that an agent could take. We can see that, going backwards is maybe not a good idea, especially if we're going backwards and then going forward again, that is going left and then going right, because then we get this -1 reward. So, it turns out what's the best thing that an agent can do? An agent probably will just want to keep going right 3 steps, right? So from here, 1, 2, 3, and we get a reward of +2 here as well as +2 here, which means that our total reward is +4. And why did I just add these rewards? Well, that's because my discount factor is -1. So I don't have to scale them by any discount. I can just add all of my rewards and I get the answer. Okay, so now that we have an idea of kind of how to, at least solve this first one, let's move on to number 2. So this is the same discount factor. We're trying to find, the V value of each of these states, except now instead of 3 steps, we're looking 10 steps into the future, and we still have an optimal agent, right? Okay, so how do we solve this? It's basically the same process. So let's first take the case when we start from A. So now we have to look 10 steps in the future. So there's basically 2 cases, right? There's one case where it goes, just all the way clockwise like this, and the other case when it goes all the way counterclockwise. There are kinds of there's intermediate cases where maybe it goes until here and then goes back or something like that, and it's useful to consider those cases. But right now it's pretty clear that what's going to happen if the agent kind of takes a few steps like this, then goes back and goes forward, is it's just going to keep getting these negative costs, right? So for example, if the agent did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's just a bunch of -1s that it's getting, right? So we can see that there's basically 2 policies, which is just go clockwise or go counterclockwise. Let's examine both of those. So what if it just goes all the way clockwise? Then that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 steps is more than enough for it to cross this entire ladder plus slide section over here, right? Which means in particular, it's enough for it to gain this -1 and -1 as well as this +2 and +2, right? So what is the total reward of an agent which ends up taking the clockwise path? It's -1 plus -1 plus +2 plus +2, which is equal to 2, right? What if it goes counterclockwise? Well, in that case, it's just all a bunch of zeros, right? And well, actually, let's see if it can make it all the way around counterclockwise. It has 10 steps, so 1, 2, 3, 4, 5, 6, 7, and at this point it cannot keep going this way because it's blocked by the fact that you cannot go up a slide. So probably it'll have to oscillate around here or something. Either way, the reward of this path is just 0, right? So the best option is to go clockwise, and so the answer for S is equal to A is just equal to 2. Okay, what if you're starting at E? You start at E. Well, in this case, once again, you can kind of think about what happens if you go left, what happens if you go right. If you go left, probably if you go left and then go right again, you're gonna have to once again collect the these -1 costs, right? So you would not want to go left. Instead, you would just want to keep going right. And where does 10 steps take you? Well, 1 2 3 4 5 6 7 8 9 10. It takes you here, which means you get both of these +2s and you don't have to get the -1s here. So that's actually great for our agent. It means that our reward is 4. And yeah, that's basically it for this row. Note that I haven't had to scale by the gamma factor because gamma is equal to 1 over here. Okay, let's continue. So the next one is v sub 10 superscript asterisk of s, where s is equal to a and e. Okay, but so it looks a lot like the previous part. The difference here is just that now we have a different gamma factor, right? So now we have a gamma factor of 0.1. And what does this mean? It means that as we kind of look into the future, so if an agent here is deciding to maybe take some path which goes up here, what that means is rewards which are closer to the start state, they're going to get multiplied by a factor of gamma raised to the number of steps away they are from the state, right? And it turns out that this has the potential of changing what is the expected future reward in each of these cases. So let's start with the s is equal to a case. So you have an agent starting over here. What is the reward that it sees if let's say it goes the clockwise path? So it just keeps going clockwise like this. Well, the first reward it sees is equal to 0. The second one it sees is also equal to 0. The third one it sees is equal to -1. The fourth it sees is -1. Then it sees +2, +2, and the rest are all 0, right? Okay, so what is the expected future reward? Well, it's going to be the first reward, which is 0. So I'll write that like this. Is going to be multiplied by gamma to the power 0. Why is it gamma to the power 0? Well, the first reward actually the first gamma factor ends up getting applied after you get your first reward. And the reason for this is, if you kind of look at like the Bellman equation or something, the way it works is usually you measure expected future reward like this. So you have r of s and a and s prime plus gamma times the v value of the succeeding state, right? So note that this reward, the very first reward that you get it without any gamma factor, right? Which is why the very first reward is multiplied by gamma to the power 0. The next one is going to get multiplied by gamma to the power 1. This reward is also 0. So far we've taken 2 steps. The third one gets multiplied by gamma to the power 2. The third reward that we had was -1. Then we had the next one multiplied by gamma cubed. It's also -1. Gamma to the power 4. This one is 2. Then you have gamma to the power 5, also times 2. And then you have a bunch of higher powers of gamma multiplied by just 0. And I'll just, I'll combine all of them and I'll write it just as 0, right? And in fact, these first ones are 0 too, so we can just, not think about them for now. So this is our expected future reward, right? Recall that gamma in this case is equal to 0.1. Okay, now what is this number going to be equal to? Well, so this thing is multiplied by gamma squared, right? What is gamma squared? Gamma squared is 0.001. So what is this entire first term? It is minus 0.001. Now this might seem small, but compare it over here with gamma to the power 5, right? That's 0.0000001. There's 5 zeros over there, right? And it's this whole thing multiplied by the number 2, right? Which means even though 2 is bigger than -1 in magnitude, right? The fact that this one is multiplied by gamma squared, whereas this one is multiplied by gamma to the power 5, means that both of these numbers are incredibly tiny compared to even just the first number, right? And so these negative terms completely overpower the positive terms, and it gives you a net negative reward for all of these terms put together, right? Because of the fact that 0.1 is a small enough fraction that when you raise it to the power 5, it makes these numbers much less than these first couple of numbers. And what does that mean? It means that the clockwise path is going to have a net negative reward for the agent, whereas the counterclockwise path is going to have a net 0 reward. So what would an optimal agent do? It's going to want to choose the 0 reward path. So the value here is equal to 0. Okay, what about the case when you start at E? So if the agent is starting at E, well, now it doesn't have to worry about those -1 rewards, right? Because it's already past them. Which means from here, it can just go forward, it can collect a +2, and it can keep going forward for the remaining steps and keep getting zeros. Now in this case also, we have to apply the discount factor. So, what's the total expected future reward? It's going to be gamma to the power 0 times 2, which is just 2, plus gamma to the power 1 times 2, which is 0.2. So what is that? That's going to be equal to 2.2. And so the final answer here is just 2.2. Plus a bunch of zeros afterwards, which I'm just ignoring because all of these are 0 reward. And that's it for this row. Okay, so the next two you will notice are Q values. So you have Q sub 1 of S West and Q sub 10 of S West, both with a gamma factor of 1. And they're both once again for optimal agents. Now the only difference between Q values and V values is that Q values also have the first action specified, right? But apart from that, they both still refer to the expected future reward, and so we'll calculate them the exact same way, just now we also have the knowledge of what's the first action we're taking. Note that because the action is west, we don't have the option of starting from A, so those are struck out. Why? Because you cannot go west from A, right? So let's just think of the first one, which is Q sub 1, that is, you're looking one step into the future. In the case of S is equal to E. Okay, so you start from E, you know that you are going west, so you go from here to here, and then, well, at this point you're basically done, right? Because you're looking at Q sub 1 and you've taken your one step, and so that's it. So now it's just basically a question of how much reward you got. And the answer is you got 0 reward, because that move gave you 0 reward. And so that's it. The answer to this is just 0, right? Okay, the next one is Q sub 10. So in this case, the first action we know is west. So you go from here to here, and then you have 9 more steps left. And once again, we'll think to ourselves, what would an optimal agent do? Well, an optimal agent probably would not go west again, because then if it wants to get any reward, it has to go east. So it has to cross this extra -1, which it would not have had to cross if it just went east right away, right? So the best thing for it to do is just to keep going east from this point, which means, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. So it crosses this -1 as well as this +2 and this +2. What's the sum of all of those? It's 2 + 2 - 1, which is equal to 3. And so the answer here is just 3. I just added them with no discount because the discount factor is equal to 1. Okay, now let's look at the next one, which is V star of S. Now there's no subscript. What does this mean? It just means that we have an infinite horizon. So there's an infinite number of steps that the agent can take, and we're thinking about what is the expected future reward of an optimally acting agent in the long run over infinite number of time steps. So okay, what about the case when we start from A? Well, we can see that one thing which the agent can do is it can just keep going clockwise, right? The actions on this MDP allow us to just keep going clockwise, and for each kind of circle that we make clockwise, we get -1, -1, +2, +2, which is a net reward of +2. So if we can keep doing this infinite number of times, then we can keep getting this +2, +2, +2, which means our expected future reward is just infinite. And that's the answer for this. What about in the case when you start from E? But if you start from E, it's the same thing. You can keep going clockwise, 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 keep getting that +2, and you have an infinite reward. So the answer for this is also equal to infinity. Okay, what about the last one? Yeah, so actually first, note that the difference between these two cases is just that now, here you had a gamma of 1, so you could just keep adding this 2, 2, 2, whereas in this case you have a gamma of 0.1. So how does this change things? In the case when you start from A, now what's happening is the same exact thing which happened to us earlier, right? The same thing which happened to us in this row over here is going to happen to us now, right? Which is because you have the gamma, this is the same calculation which is happening for calculating the expected future reward starting from A, right? These two are both weighted by gamma squared and gamma cubed, and these two are weighted by gamma to the power 4 and gamma to the power 5. And so these two numbers are so small relative to the first two numbers that the net reward of an entire circle around this grid becomes negative. And so what would an optimal agent do? It would not just keep going clockwise, clockwise, clockwise. Instead, it would probably do something like, maybe just oscillate between both of these squares or something like that, where it does not have to go through the slide and can keep collecting 0 reward. And so the optimal agent would have an expected future reward of 0, which is better than negative. What about the S equals E case? Well, now you start from here, and now you don't have to pay any cost to collect this +2 and +2 because the -1s are behind you, right? So the optimal agent would do, east, east, collect the +2s, and then maybe it would keep going clockwise until it reaches A. But once it reaches A, it's the same story again, right? So these are weighted by, 2 factors of gamma less than, this one and this one respectively, right? And so once again, after you've reached A, there's no point in making one more circle because the net future reward after that point would be negative. So the optimal agent would start from E, would get the +2 and the +2, and then would probably just oscillate between two of the squares over here, getting 0 reward for the rest of the infinite amount of time. So what is our net future reward? It's going to be the discounted version of 2 + 2, which is 2 + 0.2, which is 2.2. And that's the answer for this, and we have filled in the entire table, and we're done with part B. Okay, let's get started with part C. Basically, this question is asking us to perform Q-learning with each of the 4 samples given to us over here, and to record which of the Q values change and what they change to in this table over here. So I've written down some equations at the top. On the left over here is the general equation for how to perform an update in Q-learning. So first you have, from these quantities provided in your sample, you calculate this sample value, which is just the reward you got, plus the discounted expected future reward based on the values you've already calculated. Note that I've called this thing, so I've called this V over here. One other way of writing this would be to say that this is nothing but, so it's going to be the max over all actions of the Q value of S prime, comma the action, right? These both are exactly the same thing because the V value or the value of the state is nothing but the max over all actions of the Q values of that state along with the action, right? So these are both the same thing. So if you see this expression, you can just replace it with this mentally, right? And here is the actual Q value update. So you perform an exponential weighted average using the parameter alpha. I've written this equation in 2 different ways. You've probably seen both of these ways at some point, either in lecture or in the notes or somewhere. It's important to note that basically these equations are both the same, right? Like they're literally the same. You can get from one to the other just using, like a few steps of algebra, and you can kind of do it, mentally over here by just distributing the alpha across both of these terms. You get an alpha times sample and minus alpha times the Q value. Group this Q value with this Q value, and that's exactly what this above expression is, right? So just, nice to know that both of these are basically saying the same thing, and you can use whichever equation is convenient for you. Okay, so I've written down on the right hand side what the update looks like for the first transition. So the first transition is going from state D to state E. The action taken is east, and the reward you get is -1. So what is the sample value? It's the reward -1. plus gamma is 1, that's given to us over here, times the v value or the max over q values of the successor state. What's the successor state? It's E in this case, right? Now what are the q values of E? Well, the problem says that we can assume all q values are initialized to 0, so it's just 0, giving us a sample value of -1. What's the q update? It's 1 minus alpha, so we know alpha is equal to half, so that's half times the old q value, which is initialized to 0, plus half times the sample value, which is -1, which gives us -0.5. So what do we write in this row? Well, the q value which was updated is q of d comma east, so this thing gets updated to -0.5, and that's it for the first row. Nothing else gets updated, and that's kind of important to note, right? For each of these samples, one and exactly one value is going to get updated. It's possible that the update results in the value staying the same, right? In which case, like, basically no q value changes, but you're never going to get more than one value being updated. Okay, transition 2. So the reward you get is +2. You're going from state E to state F. The action taken is east. So let's just replace each of these quantities up here with the relevant new quantities, and let's calculate what the answer is. So the sample, what we have here is we have a reward of 2, plus gamma is still 1. What is the max over q values of the successor? Successor is F. S values have not been changed so far, which means they're still 0. So this thing is still 0. The sample value is 2. The q update is half times the current value, again still 0, plus half times the sample value, which in this case, let's replace this with 2, and the final answer here is going to be 1. So what's the update? E comma east gets updated to 1. Okay, transition 3. Again, it's the same process. So basically this problem is meant to give you practice with how to mechanically perform the Q learning algorithm. Okay, so for this one, the sample value reward is equal to 0, gamma is still equal to 1, and the expected future reward is equal to okay, so in this case, the reward is equal to 0, gamma is still equal to 1, and what is the max over the q values of the successor state? Well, the successor state is D, and we have D west and D east. D east we just updated to -0.5, whereas D west is still equal to 0. What's the max of these? The max of them is 0, so this thing is going to be 0, which means the sample value is just 0. What is the q update? It's going to be half times what's the current value of the q value of E west? Well, it's 0, so this thing is still the same. The sample value is also 0, so the q value is just 0, which means in this case the q value was not updated, right? I mean, we performed the update, but the value stayed the same, and since the question says you may leave q values unaffected by the current update blank, we're just going to leave this row blank. And let's move on to the last one, transition number 4, which is D to E. The action is east, reward is -1. Let's fill in all these blanks once again. Okay, this becomes -1, gamma is still equal to 1. What is the max of the q values of E? Well, E west at this point is 0, E east at this point is 1, so the max of them is 1. -1 plus 1 is equal to 0, which means the sample value is still equal to 0. But what is the current q value? The current q value of D east is what? It's -0.5, which means that this thing it's updated to -0.5. If you can see that. That becomes -0.5. So what's the final answer? It's equal to -0.25. And that's the answer. So you fill in the entire table, and that concludes part C. Okay, let's get started with part D, which is the final part of this question. So here we are given 3 different policies and we also have two different functions that we could potentially use for feature-based Q-learning. And the question is saying it's giving us one transition. So this is the one transition which is occurring. It's the one sample we have. And we have to decide among these three policies which of them are greedy policies for the first function as well as for the second function. So let's start with the case of the first function. I've written down the feature-based Q-learning update over here. Recall that we compute a sample value, very similar to like we did before, except this time instead of updating the Q value of the state action pair, we instead update the weights, right? So we set each old weight equal to its old value plus alpha times the difference between the sample and the old Q value times that particular function value. So for the ith weight, that corresponds to the ith function. And then how do you retrieve the Q values from these weights? Well, you take all of your FIs, you put that into a vector which you can call F, and take the dot product of that with the vector W of all the weights. And this should be equal to, so this, assuming F applies to S, A, state S and action A, this will be equal to the Q value of that state action pair. Okay, so now let's use this transition. Let's compute what the weight will be after this transition. Note that in this case, because we're considering each function separately, there's only one weight in each case because there's only one function value. So we're only going to be calculating a single W, not like W1 and W2. So let's fill in these blanks and find what the update is. So the reward is equal to 2 plus what is gamma in this case? Gamma is 1. That's what it says over here. And V of S prime in this case is G, and we have that this is the first transition which has happened, which means that all of the other Q values are currently equal to 0. So this is equal to 0 and the sample value is 2. What's the weight update? Well, it gets assigned to the old value 0 plus alpha is 1, sample value is 2. You subtract the old Q value, which was 0 because we are told that the weights were initially 0. This times the function value. Okay, so here's where we actually are using the function. The function is 1 if A is equal to east and 0 otherwise. We're evaluating this on S, A, which is F, east, and east does in fact satisfy this condition, which means the function value is equal to 1, right? Which is equal to 2. So we have that after this one transition, the weight has been updated to 2. And note that the cool thing about feature-based Q-learning is that now, even though we only found a single transition, now we have updated values for the Q values of all of these states. Why? Because for each of them, it's a different value of W, which is getting multiplied by F to find the Q value, right? Okay, so what does it mean for a policy now to be greedy with respect to these Q values? Basically, it means that for each state, you would look at what is the action which has the highest Q value for that state, and a greedy policy would have to take that action. In the case where there's a tie, it's possible that the greedy policy could take either one of the actions that is tied for the highest Q value, but it cannot take something which is below the highest Q value. So, okay, based on that, which of these are greedy policies with respect to F? Well, we can see that F is 1 if A is east and 0 otherwise, which means what is Q, what is the Q function going to be equal to? Well, it's going to be equal to W times F, which is what? It's 2 in the case when A is equal to east and 0 otherwise, right? And let's look at these right now. Basically, we want to ask ourselves the question, which of these policies always go east whenever there is the option to go east, right? And this is going to be the same as asking, is the policy greedy with respect to F? Why? Because if at some point a policy does not go east when you could have gone east, that means that they are taking this 0 over this 2. So 2 corresponds to the case of east, right? And a greedy policy will never take a smaller or an action which gives you a smaller Q value instead of one which gives you a larger Q value. So, let's look at pi 1. Well, we can see that, sometimes it does go west even when it could have gone east. So pi 1 is ruled out. Let's maybe cross that out over here. Pi 3 is also ruled out for the same reason. In both of these, the bottom row consists entirely of west, even though you could go east. Pi 2 does pass the test. So pi 2, there is only one place where you go west, which is here. And in this case, you could not have gone east. So west was the only option. So pi 2 is in fact a greedy policy with respect to the first function f. Okay, what do we do for f prime? Well, it turns out that actually the weight update is exactly the same in the case of the function f prime, because the only place where the update changes is in this value over here, because this is equal to the function value, right? But in this case, what is this function? It is 1 if the action is east and you are currently on a slide. And it turns out that, f comma east, which is this update, so f puts you somewhere over here, I believe. Actually, let's go back to the previous picture. So where does f put you exactly? F puts you, in this square over here. And that square, as we can see, is a slide, right? Which means that this function is equal to 1, so the weight gets updated to be the same thing. Okay, so now we ask the question, what does it mean for each of these policies to be greedy? It means that if a state is a slide and it is possible to go east at that state, then the policy must take east, right? So basically that's the same thing as saying, does the policy always go east on slides? And which ones are the slide squares? It's this one, this one, this one, and this one, this one, and this one. And you can see that yes, they are in fact all east for all three of these policies, which means that all three of them could be greedy policies for f prime. And you can see that this is a case when you have multiple policies which are considered greedy. So it's not the case that there has to be a single unique greedy policy for a Q function. You could have multiple. And that concludes question 5.